There we go. I've started the recording. All right. Hey, folks. So first, just wanted to remind you that the exercise set 2 is due on Friday of this week at the end of the day. I know our first exercise set was due on a Sunday. That's usually not going to happen. Usually assignments of any kind, exercises or quizzes, will have due dates or be collected on like a Monday, a Wednesday, or a Friday. Okay. So this one's due Friday. The first and second problems on this exercise set, we have pretty much learned how to do. So the first one, we're just translating back and forth, right, using predicates and quantifiers. These do involve these may involve multiple variables that need to be quantified. So sometimes you have to have nested quantifiers. Okay, just keep that in mind as you go. And then the verbal argument here is also going to, or the sort of like the proof of this argument is also going to involve quantifiers and predicates. So just pay attention to those as well. 3 and 4 are more written proofs, which you might want to do. You might want to type, possibly, or maybe not, because you know, if you want to use algebraic expressions, then you're typing your whatever word processor you use may or may not have easy to use like mathematical notation. Microsoft Word has a fairly intuitive system for doing mathematical notation. It's not the same one that I use. I don't use the built-in one. I use a different one. But you know, it's up to you if you want to type it or if you want to write it by hand. But either way, whichever way you do it, I do want you to be following the guidelines in that document I sent you guys. So regarding that document, just a reminder, you know, especially this one, the remarks on writing proofs and these sort of general considerations here, I do want you to take these to heart. So I do want you to be writing with like complete sentences, considering your audience, make sure that it's readable. I think that one of the most important things to remember that is touched on in, you know, both of these documents, both of these authors say in their work here, is that a mathematical proof is primarily a communication tool. Okay, it's not just a math problem, right? You're not just solving the problem. It's not just figuring out how to prove something. It's also communicating it to a reader. Right, so you have to be working on both of those components. And so when I'm grading, I will be grading you based on both the correctness, the logical correctness and completeness of the argument, but also the communication of it, right? How clearly are you writing, that sort of thing. So I'll be demonstrating that, you know, in class today. So let's begin. So what I have done is I've got a document up here that I'm gonna go ahead and write in, and we can go over the proofs of this claim together. We're gonna prove this claim in 3 different ways, right? So picking up where we left off yesterday, the claim is if n is an even integer, then n squared plus 1 is an odd integer. So we are assuming that we are in the domain of integers. And we have these definitions to work with, and this theorem, you know, this, I guess we could call this like a dichotomy on the set of integers. Every integer is either even or odd and never both. It's like an XOR. So here's how we can begin our proof. If it's a direct proof, we begin by assuming, we're going to begin by assuming the like hypothesis of the P implies Q statement. So looking up here, P, if this is P implies Q, P is n is an even integer. So we're going to say, assume n is an even integer. Or, you know, you could also say like, let n be an even integer, either of those would mean the same thing. Those are both common ways to begin something like this. Let n be an even integer. Let's start with that. Then we can say, well, then the first thing I want to do is immediately use the definition of an even integer. So then, and then I can say, so then n equals 2k. And can you guys see this all right, or should I zoom in a little more? Is this okay for you know, for you? Can you see it? I'm seeing
you're all good.
Yeah,
nods.
you're good.
Okie dokie. Let me know, anybody, if it's a little hard. You can always make the text bigger or something. Actually, you know, I might do that anyway. I know you guys said I'm good, but I'm just, you know, let's just make it a bit bigger. Let n be an even integer. Then n equals 2k for some integer k. So the definition of an even integer is this, basically that it's 2 times something else. Another way to think about this is that it's an even integer if it's divisible by 2, which means that when you divide it by 2, what's left is still an integer, right? So those are all the same as saying it's 2 times something else, right? And that integer may be even, or it might be odd, right? Like, so in the case of 6, for example, 6 is 2 times 3, 3 is odd. So we don't know anything about k other than that it's an integer. Now, k could be positive, or k could be negative, or k could be 0. 2 times 0 is 0, and 0 counts as an even number, by the way. All right, so there's that's kind of all we can do for now, is just say that. And so then what we might want to do is examine the thing we're trying to conclude, right? So our goal in this proof is to argue, is to be able to, you know, conclude that n squared plus 1 is an odd integer. So let's examine what that would look like. I'm gonna write, and now I'm gonna go ahead and use my math text here. N squared plus 1 equals, and you know, there was a question as to whether you need to just write out words, like do you need to write out n squared in words, like the word squared? No, you do not. So you know, even though the guidance is to use complete sentences, you could still have equations and expressions, like you can still have mathematical notation included in those complete sentences. So it's perfectly fine. And that's really what I would like you to do. So what I'm going to do here is I'm going to replace n with 2k, since we've stated that they are equal for some k, right? We don't know what k is. It could be anything, but it's something. So then we can do a little bit of algebra here, distributing the square, we get that. And then what I want to do is write this one more time in a slightly different way. Oops. 2 times 2k squared plus 1. Okay. Period. Because that's the end of a sentence. Okay, so what I have done is I have written n squared plus 1 now in the form 2 times 2k squared plus 1. Now going back to the definition of an odd number, an integer is odd if it equals 2k plus 1 for some integer k. Now the k in question doesn't need to be the same number. So actually what I want to do is, instead of write 2k plus 1, I maybe want to choose like a different letter. So instead of k, maybe we'll use L or something. That's usually what I do. If I've used k and I want to use another letter instead of k, I usually use L. So what I'm going to say next is let's let L equal 2k squared. then what we actually have on the left is n squared plus 1 equals 2l plus 1. Okay, so do you see how I did that with the little substitution? 2l plus 1 would be an odd integer as long as L is an integer. Now, is L an integer?
Yes, it is.
How do we know L is an integer?
Because its input is an even integer and you are squaring an even integer.
So an integer times an integer squared is still an integer?
Yes.
And then times 2, which is an integer as well, is still an integer?
Yes.
That's all true. So to justify that, we could cite a fact that we know about integers, which is basically that integers times integers are still integers, right? Multiplying integers together means you still have an integer. A way we can say that is this. Since integers are closed under multiplication, L is an integer. Okay, closed under multiplication means that if you combine integers together by multiplying them, the result is still an integer. The reason I'm stating why L is an integer here is because L was not already stated to be an integer. L is something that is defined using a formula, and not all formulas with integer inputs are guaranteed to give you integer outputs. Take, for example, a square root formula. If L had been defined instead of as 2k squared, if L had been defined as like 2 times the square root of k, that is a formula which, although it might have an integer input, is not guaranteed to have an integer output. So, as long as you're just multiplying or adding integers together, you're guaranteed to still have an integer. Okay, so that's something you can keep in mind for later. I'll just put a little note down here for the notes. Note: integers are closed under addition and multiplication. That means anytime you add or multiply integers together, the result is still an integer. That's what it means to be closed under an operation. Okay. Okay, pause. There's a question. How do you know what outside facts you can use in proofs aside from the definitions and theorems that I give you? Good question. It requires a bit of discretion. Basically, anything you've learned in pre-calculus or algebra is fair game. For them, yeah, pretty much. But I think the best answer is, if you are ever in doubt, just ask. Yeah, just ask. And you can also look at examples. And so if you see something being used in a lot of examples from the textbook and a lot of the examples I'm showing you in class, then you can use it too. Okay.
To elaborate on that, you mentioned a limit of stopping at pre-cal. Is there a reason for that?
No, not really. I mean, just because that is sort of the. I mean, well, the reason I didn't mention calculus is because there's going to be almost no calculus in this class at all. But I know that you've all taken pre-calculus, so that's sort of the level of expectation. If there's anybody in here who, for some reason, has taken like a mathematical analysis class, or God forbid, like, not God forbid, because this class is awesome, but like, I'd be surprised, like a abstract algebra class, I don't want you guys to be using stuff from those like higher level math classes. Does that make sense? Just because I kind of want to level the playing field and have us all working at about the same level. Yeah. So what we've done here now is we have written n squared plus 1 in the format 2 times an integer plus 1, which is by definition an odd integer. So I can write thus n squared plus 1 is an odd integer. And that's the end of the proof. So I might finish up by saying something like, therefore, whenever n is an even integer, n squared plus 1 is an odd integer. Just a restatement of, just sort of a restatement of the original claim we were trying to prove in its general form, right? You could read and interpret this paragraph as being about some particular but arbitrary even integer n, and then read this as like a universal generalization of that. Okay, this is basically using one of the rules of inference we learned. Hang on, let me just pull it up. Oops. Yeah. Universal generalization, UG, down here. So it says, if you can say something about C for an arbitrary C, which C represents like constant, right? It's sort of like a particular element from the domain you're working in. But if it's arbitrary, which means that you never specified what it is, if you know some fact about an arbitrary element, then you know it's true for all. And the fact, and that's really keys. It's really the fact that the element was arbitrary, which allows you to generalize it and say, well, since it could have been any element, the fact that we've shown is true for all elements. That's how a lot of these proofs are written. Proofs about proofs that are like universal, right? Universal claims. This is something that's true for all integers n, right? And here we were working with an arbitrary integer. I could have actually included the word arbitrary for even greater clarity. Right there, let n be an arbitrary even integer. And then this universal generalization, whenever n is any, I even could have said it like this, whenever n is any even integer, n squared plus 1 is an odd integer. Like that's, using those words there, arbitrary and then any there, kind of like really clear, like really drives home that generalization that we're making from the arbitrary element. Anyway, you don't necessarily have to write it exactly like that. I think it's pretty clear even without those minor changes, but maybe just made it extra clear with that. So this is our first proof. Any questions on this one?
I guess I've got like a general question. Like for even integers, that they equates to 2k for sub integers of k. What is k supposed to represent?
Well, it could be any integer. So like, let's take, for example, 12. 12 is an even integer. 12 is equal to 2k, where k in particular is 6.
Right.
How about negative 10? negative 10 is an even integer. Negative 10 is equal to 2 times k, where k is, in that case, negative 5. So
Right.
the point is that if it's possible to write an integer as 2 times another integer, that's what makes it even, right? If you take something which is not even, you'll find that it is impossible to do that. Like 5 cannot be written as 2 times something, where that something is an integer. If you write 5 equals 2k, k has to equal 5 halves, or 2.5, which is not an integer.
Okay.
So that k is just, it could be any integer, really. It just, which integer it is depends on which even integer you started with. But the point is that being even means that it is possible to write it like this for some integer k.
Okay.
Let's try the next one. Proof by contraposition. Okay, so this is an alternative strategy to prove a statement of the form P implies Q. We're just going to leverage the equivalence. P implies Q is the same as equivalent to not Q implies not P. So basically, if we want to prove that P implies Q, we can begin our proof by assuming not Q, and then work towards deducing not P. Let's start our proof like this. We will prove the claim by contraposition. State what we're going to do, and then we'll say assume the negation of the conclusion. N squared plus 1 is not an odd integer. And one of the things I want to do here is I want to make sure that we are still going to stay within the domain. Okay, so this is sort of a choice on my part here. We're going to stay within the domain of integers. So I'm going to include a little bit here. Assume for an integer n that n squared plus 1 is not odd, I guess. I mean, we could say not an odd integer, but that seems a little redundant. But it's not odd. Okay. Now we can use the dichotomy. Every integer is either even, X, or odd, right? So we can say, well, then by dichotomy, I guess we could say by like, what's the even or oddness is the even or oddness of a number is called parity. So that sounds kind of fancy, but it's sort of fun. Then by parity dichotomy, n squared plus 1 must be even. This is the sort of thing that sounds obvious. But you got to be careful with dichotomies. Not everything is a dichotomy. For example, even and odd is a dichotomy on the set of integers, but not on the set of real numbers. So if we are working in the domain of real numbers, saying that something is not an odd integer is not equivalent to saying that it's an even integer, because it could be not an integer at all. So there's like that third option, you can only like go to the other when it's a true dichotomy. Bilal?
So for proof by contraposition, the Q will be like the first step we do is like we assume the conclusion, right?
We assume the negation of the conclusion.
Yeah, that's what I mean, like the negation of the conclusion. We don't assume the negation of the hypotheses, right?
Correct. Yes. Yeah.
Okay.
Good call. Sometimes you might think something is a dichotomy, but it's not. For example, an integer which is not positive cannot be assumed to be negative. Why? Why is positive and negative not a dichotomy on the set of integers? Ibrahim's got it in the chat. Because of 0. Okay, so that's just a little like aside. Like there's an example of something that people often mistake as a dichotomy, but it's not, right? Even and odd is a dichotomy on integers, but positive and negative is not. Anyway, so that's why I was very clear about that. Okay, so now we have n squared plus 1 is even. So now we can use our definition again. Then, by definition, our n squared plus 1. I think I have. There we go. Oh, why does that look so big? N squared plus 1 is equals 2k, right? For some integer k. All right. So we're getting close. So maybe what we want to do now is a little bit of algebra. Instead of n squared plus 1, why don't we subtract the 1 over to the other side and get n squared equals 2k minus 1. Oops. And then maybe write that as, so 2k minus 1 is like almost the same as 2k plus 1, but it's not quite right. Like, so maybe what we can do is write that as 2k plus 2. How do I want to do that? 2k minus 2 plus 1. I know that's a bit weird, but -1 is -2 plus 1. And then I can factor out a 2 and say 2 times k minus 1 plus 1. Woo! Okay, so then by subtracting 1 from both sides, we have this. N squared is equal to 2 times, and the reason I did this little sort of gymnastics with my numbers here is because I wanted to get it into the format of 2 times an integer plus 1, which is the, very specific definition of an odd integer. So I can say now, since k minus 1 is an integer, I mean, maybe what we could do that is, again, I'll cite closed under integers again, right? So since integers are closed under addition and subtraction, k minus 1 is an integer. So then now we have n squared is an odd integer. Okay, we've come to this point now. We've got n squared is odd. Now, remember what our goal is? Our goal is to deduce the negation of the original hypothesis. So going back up to our claim we're working on, the hypothesis was n is an even integer. So we want to show somehow that n is not an even integer, which we know now because of that dichotomy, that means n is an odd integer. So far we've been able to show that n squared is an odd integer. How can we prove that n is an odd integer? I mean, I think what we want to do here is just prove like a second little result, like a little result that we can use like a theorem. It's almost like I wish we had another theorem here to work with that said an even integer squared is even and an odd integer squared is odd, right? Well, do you think we can prove that?
Pretty easily.
Let's prove that. I think that seems like a pretty easy thing to do. So in order to prove that, what I want to do is actually come up here and prove what's called a lemma. So the thing we're working on right now is a theorem. We can call this a theorem. And it is this: if n is an even integer, then n squared plus 1 is an odd integer. But before that theorem, we want to prove another theorem, a smaller theorem, which we're going to call a lemma. A lemma is a word for a sort of a little theorem, which might not be as interesting on its own, but it's sort of like it's like useful. It's useful. It's a useful tool for solving for proving the next theorem. Does that kind of make sense? It's like actually, if anything, I think this lemma is more interesting than the theorem. But the point is, we are proving this lemma as a tool for the purpose of so that we can cite it down here. So this is going to be an even integer squared is even, and an odd integer squared is odd. Okay, this will be a pretty quick thing to prove. We can say this. We can break this into cases. Case 1, if n is even, then n equals 2k for some k, some integer k, and thus n squared equals 2k squared, like we did before, which is 4k squared, which is 2 times 2k squared. Like before, since that 2k squared is an integer, n squared is therefore even. And then we do case 2. If n is odd, then n is 2k plus 1 for some integer k, and thus we can do the same thing. Oops. N squared is going to be 2k plus 1 squared, and now if I FOIL that out, I get 4k squared plus 4k plus 1. Did I do that algebra right? 2k squared, 2k plus 1 squared is 4k squared plus, yeah. And then 2 plus 2 is also 4k plus 1, yeah. And then I can do a similar thing here where I want to write that as 2 times something plus 1. So if I factor a 2 out of the first 2 terms there, let's move this out so you can see my algebra a little better. Okay, if I factor a 2 out of the first 2 terms, I've got like 2k squared plus 2k, right? There we go. And then similarly, the number we have in there, 2k squared plus 2k, that's all just integers added and multiplied together. So again, we can say, since that little bit there is an integer, now we have n squared is odd. And that concludes that proof. I'll end with a little QED over on the right-hand side. It's kind of a traditional way to end a proof. It's an more old-fashioned way, but it's a way. So that was like a quick little lemma, right? So now we can say, let's call this lemma 1. Okay. And so now in our theorem, we can cite that lemma, right? So we can say, oh, you know what we should have done actually is we should have done a little better than this. I'm just realizing that actually the lemma we proved isn't exactly what we want, because we don't want to be able to say, we don't actually want to be able to say like, since this says basically if n is odd, then n squared is odd, right? We actually want to go the other way around. What we actually wanted was the opposite of that. We wanted if n squared is odd, then n is odd. But thankfully, that's a contrapositive of this first statement here. So in my theorem down here, what I'm going to say is by lemma 1, if n is even, then n squared is even. Well, the contrapositive of this claim is, of this statement, not claim, is that if n squared is not even, then n is not even. But again, by dichotomy, this means that if n squared is odd, then n is odd. So what I actually proved in the lemma, right? What I actually proved in the lemma is that an even number squared is even. We wanted the converse of that sort of thing, or we wanted, I guess we wanted the converse of this, which is sort of the contrapositive of this. And so we can get that. I just had to do an extra step. I had to do this contrapositive idea here in order to get sort of the backwards. What I'm saying is that I had my arrow kind of pointing in the wrong direction in the thing that I proved. I wanted to go from n squared back to n, and that required flipping the arrow around, right? But contrapositive does that, doesn't it? It flips the arrow in the other direction, which, so that worked out. So now that we got that, we can say n is odd. So I think we can finish by saying, well, we deduced the negation, maybe we could say this, from the negation of the conclusion, we deduce the negation of the hypothesis. Thus, by contraposition, the claim is true. The original claim. Whenever n is even, n squared plus 1 is odd. Good. Okay. What do you think of that one? Slightly more complicated, a little bit. I mean, it kind of was, right? Because I decided to do it in the format of this sort of lemma here, because we encountered the situation where it was like we needed to get from n squared back to n, right? Instead of moving from n to n. From n to n squared is pretty easy because like in the direct proof, we could just substitute something in, right? We just plugged in 2k and did some algebra. But getting from n squared back to n is a little bit harder than that. And I decided not to do any square root shenanigans, right? I very explicitly avoided square roots because square roots, as I pointed out earlier, do not always result in an integer output. And I didn't want to get messy with square roots. So that's why I didn't do that. Anyway, I will go ahead and post these on D2L, post what I've written here. So I think that's what you're asking about, Nicholas, right? Well, yeah, so this will be posted. Yeah. So questions. So Bilal, you had your hand raised earlier. Did you still have a question, or did you is your hand still up? You're okay. And then Kyler, you've got a hand too.
Got an application question here. Why might I want to use the contraposition versus the just standard claim method?
Just a direct approach? Oops.
Yes.
Great question. The reason is that sometimes statements are easier to prove by contraposition than they are to prove directly. Okay. So, for example, if the original claim had been if n squared plus 1 is even or is odd, is even, then n is odd, right? If that had been the original claim, this proof would be the direct proof. And the contrapositive would have been easier. Like the contrapositive would have been the one that we were calling direct, right? We call this the direct proof because the claim was written in that order. But if this claim had been flipped around, and like if we were trying to prove, if the original claim that had been presented to us was the contrapositive of this, then this claim would be the proof by contraposition. Get what I'm saying? The easier one would have been the proof by contraposition. So my point is, it really just depends. It really just depends on what you're trying to prove. Sometimes one way is easier, sometimes the other way is easier, and you just got to kind of consider both and choose the one that looks and sounds easier to do. And that is just going to come with experience, just more examples, more practice. The more you practice doing both directions, you get kind of a feel for, first of all, you get practice stating the contrapositive of something. And if you can flip back and forth between an if-then statement and its contrapositive, because those are equivalent, you can then easily choose whichever one is more convenient to work with. And so that's just like you've got both available to you. Does that make sense? I agree that this was a harder proof. So, Cameron?
Oh, whoops.
Okay. We only have a few minutes, so I want to make sure we get to our third and final proof strategy. This is proof by contradiction. So proof by contradiction is a more general strategy here that is not just for implication statements, improving if P then Q. A lot of the claims we'll be proving in this class are in that form, P implies Q, but not all of them. Some of them are just going to be like, there exists something, or, I don't know. Some of them aren't phrased with an if then. So just a very general proof strategy is to say, hey, you want to prove something, call it P. What you can do is assume the complete negation of P. And from that negation, try to deduce something ridiculous, something that's clearly just false, a contradiction. And if you can do that, that actually proves that P must have been true, right? Because the negation can't possibly be true if it allows you to conclude something clearly false. The negation must be false, so the original statement must be true. This comes down to this little propositional equivalence, which I actually had you guys prove on your exercise set 1. So you guys on exercise set 1 proved this, which is the foundational logic behind proof by contradiction. Okay, not B implies F is equivalent to P. So what we want to do here is begin by saying something like, you know, we will prove the claim by contradiction. Assume the claim is false. And now we're going to state the negation of the claim, right? What was our claim again? It was this. Oops. I've been calling it the claim here. So how do we negate that? You guys remember how you negate if then?
Isn't it P or not Q?
Close.
Oh, it's not P or Q, isn't it?
It's no, you were right with the not. You had the negation in the right place, but you said or. It's and. It's P and not Q is the negation. What you do is you use the fact that this is equivalent to not P or Q, right? And then you negate that or with De Morgan's law, and De Morgan's law turns it into an and, as well as swapping the negations around. Right, so that's what we want. And so that's going to look something like n is an even integer and n squared plus 1 is an odd integer. That's what we want to start by claiming, by assuming over here. Assume the claim is false. N is an so we're going to say, you know, we can assume n is an even integer and n squared plus 1 is an odd integer. Okay, so yeah, so it's like it's a little bit different. It's a little bit different than what we had over here. And I might actually it's very similar to what we had over here. So I might kind of like just refer or even copy paste some of this. I just realized I'm missing a not somewhere, aren't I? Hang on a second. If n is an even integer, then n squared plus 1 is an odd integer. I want to say is not an odd integer. There we go. I forgot the negation. Okay, we got to have that in there. Is not an odd integer. There we go. So that means that you know, again, by dichotomy, dirty dichotomy. So fun to say. That n squared plus 1 is even. So I'm going to scroll back up here. We were able to prove earlier that if n squared plus 1 is even, then n is odd. I'm going to copy that whole part right there and stick it down here. Okay. So we proved earlier, if n squared plus 1 is even, right, then n squared plus 1 is 2k. And from that, we were able to show that n squared, then n is odd, okay? Or alternatively, going back to the direct proof, from the direct proof, we were able to say, hey, if n is an even integer, then n squared plus 1 is an odd integer. Right? Either one of those, right, give us a contradiction. We have a contradiction, which is this: n cannot be both even and odd, right? Because part of our assumption, I'm going to highlight here, part of our assumption there is that n is an even integer. But through this argument about n squared plus 1 being odd, we were able to conclude that n is odd, right? Those can't both be true. Or alternatively, looking at the parenthetical version of this, n squared plus 1 cannot be both odd and even, right? We started with it stating that it's odd, and this argument we did earlier showed that it was, sorry, we started by saying that it must be even, and this argument showed that it's odd, right? So in either case, that contradiction says that the original assumption must have been false, and thus its negation must be true. What is that negation? It's the original claim. Pick up that word, it's a bit confusing. The assumption must have been false, and thus its negation, the original claim we're trying to prove here, must be true. And that's the essence of, yeah, if you got to head out, no worries. This is recorded. Oh, is it recorded? Shit, I forgot to record. Oh no, I remember to record. Now I said shit on a recording.
For shame, Professor.
Yeah, this is the essence of proof by contradiction, right? It's like you assume the negation and then you are able to deduce something that's clearly false. And so you say, well, that thing I assumed must be false. And if that was false, then the original thing must be true. Yeah. All right. Okay, folks, see you in class again tomorrow. I don't know what we're going to do, but I might end up actually just sort of lecturing tomorrow, just showing you guys some more examples. I have a lot more proof examples that I could show you. So we might just kind of focus on that. We'll see. But until then, I will be available by email and office hours. Bye, folks.
Have a good day.
Thank you. You too.